Welcome to the deep dive. We're plunging into, well, the incredible amount of information that surrounds us every single day. If you've ever felt like there are powerful insights just hiding beneath the surface of all that data, you're definitely not wrong. Today, we're going to try and unlock those secrets. The hidden data patterns. We're talking about those invisible relationships, the underlying trends, the surprising structures within raw information. And when you uncover them, they can transform data into something really powerful, actionable intelligence. So our mission today, to give you a shortcut to understanding how artificial intelligence, AI, is uniquely equipped to find these elusive patterns and what that really means for you right now.
And that hidden part is absolutely key. We're not talking about patterns you can just spot by, glancing at a spreadsheet.
Yep.
Or even with a whole team manually sifting through numbers. Our human observation is it's incredibly limited by the sheer volume, the complexity of modern data. As one analysis we looked at put it perfectly, columns of numbers are not very good ways to find patterns. There's just too much. So this is where AI-powered pattern recognition really steps in. Think of it like a technological extension of our own pattern spotting abilities, but scaled up massively. It's designed to process these huge data sets and extract the meaningful melody out of the static, so to speak. It takes abstract data and gives it the color, the texture, the symbolic meaning you need for real interpretation.
I love that, finding the melody. So let's unpack this a bit. What exactly do we mean by a pattern in data? It sounds simple, but it's actually pretty nuanced. When we talk about these hidden patterns, we're mostly looking at three broad categories: statistical, structural, and behavioral or sequential. And as we go through them, maybe you can think about how these might be playing out in your own daily life, sometimes in ways you haven't really noticed.
Absolutely. So let's start with statistical patterns. These are really about the numerical properties of the data. You've got trends like the obvious spike in online shopping during the holidays. That's a clear trend. Then correlations, that's the relationship between variables. Think about, say, hours studied versus exam scores. Usually more hours means higher scores, right? You can plot that on a scatter graph. And distributions, which show how data points are spread out, like in a histogram.
Okay, so trends, correlations, distributions, those feel somewhat familiar, maybe from spreadsheets. But you mentioned two others where it sounds like we're diving deeper. What's really fascinating within statistical patterns?
Right, this is where it gets really interesting. We start looking for clusters. These are natural groupings of data points, things that are more similar to each other than they are to stuff in other groups. A classic example is identifying different customer segments based on how they shop. Cluster analysis can find those groups. And crucially, we look for outliers and anomalies. These are the data points that stick out, the ones that deviate significantly from everything else. Now, these aren't usually just errors. Often they're highly informative signals. They might point to fraud or a rare event or maybe a system glitch, something that definitely needs a closer look. It's like finding treasure in what looks like noise.
Yeah, I like that, turning potential errors into valuable clues. Okay, so beyond the numbers, what about structural patterns?
Right. Structural patterns go beyond just the numerical values. They focus on the organization, the relationships within the data itself. Think about mapping out a social network by looking at who talks to whom. That's structure.
Yeah.
Or maybe uncovering really sophisticated hidden connections between accounts or transactions that seem totally unrelated. A human might never spot those links in a huge data set, but AI can reveal these complex webs.
Oh, that makes sense. And the final category, behavioral and sequential patterns. I'm guessing that's about things happening over time.
Exactly. This category focuses on patterns that unfold in sequence. So you might see specific sequences like the common paths people take clicking through a website before they buy something. Super useful for optimizing that flow. And then you have association rules. These are the classic if-then relationships. The most famous example, market basket analysis. Finding out the customers who buy bread and milk are also very likely to buy eggs. It seems simple, but that kind of insight powers tons of recommendation engines you see online, suggesting movies, products, you name it.
That's a great overview of what we're looking for, these hidden threads. Now let's shift to the how. How does AI actually go from all that raw, sometimes messy data to these deep insights? You mentioned there's a general pipeline, data collection, then pre-processing and feature extraction, then pattern detection or model training, and finally making classifications or decisions.
Right. And what's really fascinating is how AI handles those middle stages, feature extraction and pattern detection, especially in deep neural networks. It's all enabled by this concept of hidden representations. These are abstract internal features the network learns while it's training They live in its hidden layers. They're called hidden because you don't directly see them as inputs or outputs. They're the model's own internal way of understanding the data.
So is it kind of like how our brains build up complex ideas from simple things, like seeing lines and curves, then letters, then words, then meaning? Is that a fair comparison?
That's an excellent analogy, yeah. These layers progressively transform the raw input into something more abstract, more useful. Each layer learns patterns from the layer before it, creating this hierarchy of features. Just like our own cognitive systems build complexity. Take a convolutional neural network, a CNN, for image recognition. Input is just pixels, right? The first hidden layer might learn simple stuff, like edges or corners. Deeper layers combine those to learn more complex things, like maybe the shape of an eye or the texture of fur. And then the final layers put it all together to recognize cat or dog. This ability to automatically learn these feature hierarchies without explicit programming, that's the magic behind deep learning's success.
That automatic feature learning sounds incredibly powerful, but I've also heard people talk about the black box problem with AI. What's that about? Is it like a flaw?
That's a really important point you bring up. This power, this abstraction, it does have a consequence. The very complexity and abstract nature of these hidden representations makes them really hard for us humans to interpret directly. That's the black box problem. It's not necessarily a flaw, though. It's more like an inherent consequence of how powerful these models are. To get human-like performance, the model creates representations that are as abstract and nuanced as our own thoughts, which makes them just as hard to explain simply. It's about depth, not defect.
Okay, so we have these amazing models learning complex representations, but how do they actually learn? That brings us to the main machine learning approaches: supervised, unsupervised, and deep learning. Different ways AI learns those patterns we discussed.
Exactly. So supervised learning is like learning with a teacher. The model gets trained on data where every example is already labeled with the right answer. So you feed it thousands of emails already marked spam or not spam. It learns the patterns and separate them. Then it can predict if a new email is spam.
Got it. Learning from clear examples to make predictions. What about unsupervised learning? You mentioned venturing into the unknown.
Yeah, unsupervised learning is different. It's like exploring data that doesn't have labels, just looking for inherent structures or groups on its own. This is super powerful for discovery, especially when you don't know exactly what you're looking for. For example, a retailer could use it to cluster customers into different groups based purely on their shopping habits, without telling the AI beforehand what those groups should be. It also includes techniques like dimensionality reduction, like PCA, principal component analysis.
PCA, okay, that sounds technical. Can you give us a quick, maybe non-technical reason why reducing features or dimensions is useful? Why simplify?
Good question. Think of PCA like sketching the main outline of a really detailed drawing. Instead of describing every single tiny detail, you capture the most important shapes and lines with just a few strokes. You lose some minor details, but you keep the essence. Simplifying like this is powerful because it cuts through the noise, makes the underlying patterns clearer, and makes really complex data much easier to work with without losing the crucial information.
That's a great explanation. Okay, and the last category was deep learning architectures. We touched on CNNs for images. What else is in there, and what makes them game changers?
Right, deep learning architectures, as we hinted, are what really push pattern recognition forward. CNN's great for spatial data like images. For sequential data, things like time series, text, speech, we have recurrent neural networks or RNNs. What's special about RNNs is they have a kind of internal memory. They can keep track of past information in the sequence. That makes them perfect for patterns that unfold over time, like predicting the next word in this sentence you're hearing.
Makes sense for things like language, where context matters. And what about embeddings? That term comes up a lot, especially with large language models. How do they fit in?
Embeddings are a really powerful, more advanced concept, especially in NLP, natural language processing. Essentially, words, or even items like products, get represented as dense vectors, lists of numbers in a high-dimensional space. But the key thing is, these numbers aren't random. They capture semantic meaning, relationships. So the vector for king and the vector for queen will be mathematically closer to each other in this space than, say, the vector for apple, because king and queen share that royal context. This ability to represent meaning mathematically is fundamental to how modern search engines and LLMs actually understand and process language.
Which brings us perfectly to the practical impact. This isn't just theory. It's about where these hidden patterns are genuinely changing the world. And it's not just about automating tasks, right? It feels like a real step change in what's even possible, going beyond what humans alone could do.
Precisely. Let's look at healthcare. AI spotting hidden patterns here is literally saving lives. In medical imaging, those CNNs we talked about are transforming diagnostics. They help analyze mammograms for breast cancer, picking up on subtle visual cues that distinguish healthy tissue from cancerous tissue, sometimes things the human eye might miss.
That alone is massive.
Yep.
But didn't you mention something even more startling with eye scans earlier?
Yes, this is where it gets truly groundbreaking. There was a major collaboration, Moorfields Eye Hospital and DeepMind. They developed an AI that analyzed OCT eye scans. Not only did it achieve 94% diagnostic accuracy matching top specialists, but, critically, it could predict the future progression of a degenerative eye condition before any clinical signs were visible to human experts.
Wow, before humans could even see it, the potential for early intervention there is just huge. It's like a medical crystal ball.
It really is. And then there's neurological event prediction, using RNNs to predict epileptic seizures from EEG data. Research shows these models can achieve high sensitivity, over 90%, and specificity around 89%, and the processing time, around 12 milliseconds.
12 milliseconds, that's practically instantaneous. The potential for giving someone a warning, improving patient safety, it's incredible.
Yeah.
Okay, what about outside healthcare? How's this changing, say, finance?
In finance, AI is really reshaping things, both for security and access. Take proactive fraud detection. Old systems use static rules which fraudsters learn to beat. AI systems build a dynamic, multidimensional baseline of what's normal behavior for a user or transaction. Any subtle deviation, even a completely new type of fraud pattern, gets flagged in real time. This involves analyzing things like behavioral biometrics, how you type, maybe, and network analysis to find hidden links between fraudsters and big rings. The result? Fewer false alarms, and actually stopping fraud as it happens.
So it's not just catching the obvious stuff, but the really sophisticated, novel attacks. How does this affect everyday things like getting a loan or insurance?
That ties into algorithmic credit scoring. Traditional models often struggle with people who have thin credit files. AI can look at a much broader range of data, including alternative sources like, say, rent payment history, to get a more complete picture of risk. There's a compelling example from PPS Insurance in South Africa. They used an AI platform that could match personalized insurance offers to customers in minutes. Before AI, that process took 1 to 3 months of manual work. They saw a 5% jump in sales almost immediately just because they could respond so much faster.
Months to minutes. That's a massive operational leap. Okay, one more area. Environmental science, giving us a global view on huge challenges.
Absolutely. In climate modeling and weather prediction, AI is helping improve these incredibly complex, computationally heavy models. It learns better parameterizations, basically, smarter approximations for small-scale processes by studying high-resolution simulations. This leads to more robust long-term climate models and more efficient, accurate weather forecasts. That impacts everything from farming to disaster prep. And for monitoring deforestation and pollution, think satellite images plus CNNs. AI can automatically spot land use changes, illegal logging, early signs of wildfires across huge remote areas. Same goes for monitoring air and water quality at scale. It provides timely data for conservation, for policy decisions, in a way that just wasn't possible before at that speed and detail.
These applications are genuinely transformative, seeing patterns, getting insights that were totally invisible just years ago. But with all this power, what about the risks? We touched on the black box nature earlier. That complexity must lead to challenges.
That's right. When you're dealing with systems this powerful, there are definite technical hurdles to be aware of. First, the classic garbage in, garbage out. AI quality is totally dependent on the training data. If the data is bad, incomplete, biased, the model will be too. Then there's the sheer cost, computational and environmental. Training these huge models takes immense processing power and energy. And finally, model brittleness or overfitting. An AI might learn its training data too well, so it fails when it sees new, slightly different real-world data. Or it might react unpredictably to tiny changes in input that makes them potentially unreliable. And beyond those, you've got big privacy questions with all that data and complex issues around accountability when autonomous systems mess up.
Right. So given the black box and these technical challenges, how do we move forward? How do we build trust, ensure these systems are reliable, especially when we can't always peek inside? That's where explainable AI or XAI comes in, right?
Exactly. It really tackles that core question. How can we understand why an AI made a specific decision, especially for critical choices? The field of XAI distinguishes between interpretability and explainability. Interpretability is for models that are naturally transparent, like a simple decision tree where you can follow the logic step by step. Explainability is for those complex black boxes, like deep neural networks. We need special post-hoc techniques to get an approximation or summary of why it reached a conclusion. And this is absolutely vital in fields like healthcare. Doctors need to trust a diagnosis, or finance, where regulations often demand clear reasons for denying credit, for example.
Makes total sense. We need the why. So what are some of the actual techniques people are using for this?
Two of the most prominent techniques right now are LIME, that's Local Interpretable Model Agnostic Explanations, and A-Shape, which stands for Shapley Additive Explanations. LIME is cool because it's model agnostic. It works on pretty much any AI model. It works by creating a simpler local model just to explain one specific prediction. So if you want to know why this particular image was labeled cat, LIME can highlight the pixels in that image that push the decision towards cat. Makes it quite intuitive for debugging.
Okay, explaining individual predictions locally. And A-Shape, how's that different?
Shape Hay has a more rigorous foundation, based on game theory, actually. It provides a mathematically fair way to distribute the credit for the final outcome among all the input features. What's powerful about A-Shape is it gives you both local explanations, like LIME, but also cohesive global explanations of the model's overall behavior, how it generally weights different factors.
Yeah.
So, back to the medical example. A CNN flags a mammogram as potentially malignant. A-Shape E or LIME could generate a heat map showing the exact pixels, maybe a suspicious mass, that influence that decision. A radiologist can then instantly see the AI's reasoning and verify it. Or, for a loan denial, A-Shape could show exactly how much a high debt-to-income ratio contributed negatively versus how much a low credit score did. Clear, actionable feedback for the applicant.
Okay, so if I'm getting this right, XAI is basically a diagnostic tool. It helps us understand how the AI is thinking, helping ensure it's accurate and reliable.
That's a great way to put it. It's a diagnostic tool. It can brilliantly expose how the model is using the information. For instance, if XAI shows a credit model is really heavily weighting something seemingly minor, you can investigate why. Is that variable genuinely predictive, or is something weird happening? But, and this is crucial, XAI reveals the how. It doesn't automatically fix any problems like unreliability or bias. The responsibility then falls squarely on the human developers, the stakeholders, to use that transparency to take corrective action, to make sure the model is working as intended and is trustworthy.
Okay, so looking ahead now, how is AI pattern recognition still evolving? What's on the horizon in this incredibly fast-moving field?
Well, it's definitely not slowing down. We're seeing really interesting emerging paradigms. Things like agentic and self-evolving AI. Think about virtual coworkers. AI agents that can understand a high-level goal, break it down, and then autonomously use different digital tools to get it done. We're moving towards systems that can potentially adapt and improve their own algorithms over time, continuous learning, and generative AI. We mostly hear about it creating text or images, but fundamentally, it's an incredibly sophisticated pattern recognition and prediction engine. It's finding new uses way beyond content generation in areas like drug discovery, material science, complex system modeling. And importantly, the focus is really shifting towards new human-machine collaboration models. It's less about replacing humans, much more about augmenting them. AI is a co-creator working alongside us. Architecturally, the future looks like distributed hybrid ecosystems. So you'll have these massive centralized brain models, like the big LLMs, working together with smaller specialized nerve-ending models deployed right out at the edge on IoT devices, smartphones, etc. This gives you a balance between raw power and efficiency, plus real-time responsiveness where you need it, and the market growth. It's just staggering. Global AI software market projected to hit nearly $300 billion by 2027. Generative AI is a huge part of that. Investment is massive. AI is seen as foundational and amplifier for almost every other tech trend. But we connect this to the bigger picture. The strategic imperative now is all about responsible innovation and robust governance. Trust is becoming the single most important factor for widespread AI adoption. Ensuring these systems are reliable, transparent, effective. That's not just nice to have, it's core strategy for any organization using AI.
We've covered an incredible amount of ground today, from the basic idea of hidden data patterns to these really transformative applications changing entire industries. It's clear AI brings immense power to understanding our world.
Indeed. But as we've discussed, that immense power carries profound responsibilities. The black box challenge, the data quality issues, potential brittleness. These aren't just technical puzzles. They force us to make very deliberate choices about how we build and deploy these systems to ensure they're reliable and truly deliver on their potential benefit.
Absolutely. It feels like the ultimate success of AI won't just be measured by its accuracy, but by our wisdom in guiding its development, making sure it's transparent, reliable, and genuinely aligned with human progress. So the question to leave you with is, What new, maybe more profound questions will AI allow you to ask about yourselves and about the world around us?
This is DigitView.